Hello everybody. We're still talking about the liquid extraction. In the previous videos, we showed how we can calculate the variables that we don't know that are going into the system and coming out of the system, which were mainly V1 and Ln as a flow rates and as compositions. And now we need to go to the next step, which is calculating the number of stages. And to calculate the number of stages, we actually need to know how to draw the operating line, and this is what we're gonna do today. So the operating line, as we proved before, it's gonna be on the ternary diagram, it's gonna be straight lines passing by a point here on the raffinate curve and another point on the extract curve, and this is how the stage will look like. It's gonna be like L node and V1. It's gonna be like Ln and Vn plus 1, and we proved that all the operating lines would intersect in one point, which is the point O. And we took advantage of this by knowing how we can predict or get the next stage, which is by getting the L1, which is the solute stream that is in equilibrium with the solvent stream V1. I would recommend you go back to the previous videos and see the flow sheet to understand. If you don't understand it clearly here, you would understand it clearly when you look at the flow sheet. And then the next stage would be and this is important actually to keep in mind, which is how to get the next stage. So we connect L1 and O, and the intersection with the extract curve would generate the point V2. And we will go again and again and again till we cross the Ln Vn plus 1, and this is how we can get the number of stages, which is going to be 3.5. Of course, these are actual stages because we are assuming that each stage will go to equilibrium. One thing that we talked about also before is how to get the minimum solvent rate, which is the solvent rate that you cannot use or use less than this value. We said that this is the value of V1 that will make the operating line for the first stage overlapping over the tie line, and in this case the operating line is exactly the same as the equilibrium curve or the tie line. In this case you'll have no driving force. So this is one other thing that we will see today, and we saw that it's gonna be easier to draw all the things on the 45 or I mean the XY diagram, and this is what we did in the previous video, that we showed how we can draw the equilibrium curve on the XY diagram. And then the next stage or the next step is to draw the operating line, and the operating line would be simply doing the same thing, but instead of doing it for the tie lines, is going to be done for the operating line. So for instance, L node V1 line would be like this. So we'll have one point here, and then we will have one point here. We can connect them and use the operating line as a straight line and calculate the number of stages by the same way we did before for distillation, but you can add more points in the middle by passing any random line between these two operating lines, and this line passes by O, cuts here and here, and these 2 points will be reflected here as 1 point, and then we can draw what we call the operating curve. It's gonna be an operating line actually, it's not an operating curve. So let's see how we can deal with these things in Excel. So first, drawing the operating line is going to be easy because the operating line is simply the same variables that we used before. So one line would be connecting L node and V1, which is going to be L node, this is the X, and this is the XC. It's extremely important to make the file as organized as possible, so you do not get confused with the variables that you have, or you put something instead of something else. And you see I put some good time in my work, just to format the file well and make sure that everything is clear and I can understand each and every number that is in the sheet, so I can use it whenever I want. So what I'm doing now is that I got these two lines and I want to get the point O. Actually, this is what I need to do now. And to get the point O, which is the intersection of this line and this line, I need to get the slope and the intercept. You might think that I need to draw a line here and a line here, and then these two lines, for each one of them I'm gonna draw or make a trend line and then make it linear, get the slope and intercept from the equation. But actually for the straight line, it's there is an easier way, which is just using a function called slope. You just need to define the y's and x, and that's it. And intercept, there is another function called intercept, which is gonna do the same thing, define y and x. And you have now the slope and the intercept of these of this straight line, which is L node v1. I have this slope and intercept, and the slope is negative, so it's clear that the slope should be negative here. We can copy this these two formulas, so I now have the slope and the intercept for both cases. So to get the intersection, just solve any two equations or two linear equations. There's kind of a simple form that you can get, which is going to be negative the intercept minus intercept divided by the slope minus slope. So this is how you can get the intersection of two or solve two linear equations from this the intercept and the slope. And to get the value of xc, just substitute using the value of x node, so it's going to be x multiplied by the slope plus intercept. So I now know that these two lines should intersect in the point negative 570. Just to confirm it, we can, and this is one kind of nice thing that we can learn here, that we can add one line which we will call the L node v1. Let's make it an uppercase L, and then well, the x values would be these, the y values would be these, and this is the line. So I'm gonna do the trend line thing now, because I need to show you something that's really important or good to know. So we dealt with most of these things before. We show how to display the equation, the r square and everything, but we never did the forecast. And the forecast is simply, it is showing you how the equation would behave out of this range that you defined it. So you have already chosen the equation to be linear, and you need to see how it will look like at smaller values of x. So I can make it backward by 10, for instance, and we can make it forward by 5, whatever. So you see that this is giving you different values or the shape of the curve, and at different values that you didn't enter or define while doing the trend line. So I'm gonna remove it now, because it's gonna be a lot of curves here, but I already done it before. What I'm trying to say is that you can confirm your calculations here by comparing your numbers to what you'll see on the plot. And I've already done it before or in another sheet, and you'd see this is the line and this is the line, and the intersection is between 160 and 180, which is 170, and the x is between 0 and negative 10, which is negative 5.7, which confirms what we did. So I'm kind of confident now that the next steps would be based on true values that do not have any errors. So it's good to check before you go to the next step. So now I want to move to here and to see how this will affect, or how the operating line will look like. So you can simply take the values from here. So I'm gonna take the value of 30, and the y is gonna be 12.38. This x would be 8, and the y would be 0. And I can now go here and select data and then add the operating line. So what I did here is exactly like what I did in in my presentation when I was doing these lines. So this is exactly what I did here. I took these values from here, put it here, exactly like what I did in the curve. And then I'm gonna take these x values and these y values, and you'd see it is this is how the operating line would look like. Of course, I can get the slope and the intercept of the operating line simply, and this is how the slope and intercept would look like. Let's take these so we don't get confused. Just to confirm that this line would be, or before confirming the line is a straight line, let's go to the minimum solvent rate check. So I need to check how much solvent I need. So you see here, I'd make this line thinner, just to be easy for us to tell if it is touching or not. So what will happen actually when you change it or decrease the solvent rate is that this operating line would get higher slope. The slope will be bigger, so the curve would go like this. So you need to know exactly when. So this point wouldn't change, but this would change. So you need to know at what value of V1 will it change. So I have it to 150 now, so I can try to 130. Um, the only bad thing about this is that you have V1 is not calculated automatically. You have to do a goal seek run just to make sure that you have the right value everyone. So it's not gonna reflect directly on the plot here or here. When you change it, you have to make sure that this is 0 by changing this, and this is why I have this in red, so I can easily tell which is which. So when I'm done with it, you see that the curve has already tilted more. Just to get a closer look here, this is how the curve looks. It's getting closer, but it is not touching. So I have to change it to, like, say 210 for instance, and then it's gonna take little trials, but it's not gonna be like that bad. So I'm gonna put this to 0 by changing this, and now you see it is and this is what I want you to see. It is touching, the operating line is touching the equilibrium curve. And if you look at I'm gonna add this again, just I'm gonna add the operating line on the ternary diagram so you can see how it looks like, and how the line is kind of overlapping. And this is a very good thing to keep in mind, that you have here the equilibrium relation as tie lines which are not continuous. You have tie line and then some space and then another tie line and some space. So when if you want to get the minimum solvent rate based on this the ternary diagram, you need to get it as much as you can parallel to the closest tie line. So it's not gonna it's most probably not gonna overlap over an existing tie line. So I have to look for the closest tie line and make sure it is parallel to it. So this is the only way you can do it actually, and that's why I really like this kind of way of calculating the number of stages, because you are not gonna be bounded by these tie lines anymore. You are using a continuous equilibrium curve and a continuous tie line, so you can simply calculate the stages without any issues. So now I'm gonna make it 250 as it was before, and get this into do the goal seek, and this to the value of 0 by changing this. And here we go, and you see that the curve is now the operating line is away from the equilibrium curve. And then you'd see that this line, I'm getting it closer just to make sure that it's on the ternary diagram is going right. You'd see that this is not parallel anymore to the closest tie line, which is the light green dotted line. Okay, so this confirms everything. or what I'm saying. So now the last thing is just to confirm that this is gonna be a real straight line. So it's not a curve, and I'm just getting a straight line because I have only 2 points. So I'm gonna put a point in between. So it's gonna be the x will be the average of the 30 and 8, so it's gonna be exactly in the middle. And this let me just put it here. So what I'm trying to do is to calculate, so this is where it's gonna be on the raffinate layer. I want to get this point on the extract layer. I mean the XC on the raffinate layer. So again, what I'm gonna do is I'm gonna put a point here and on the extract layer and try to predict the value or calculate the value on the raffinate layer, so that this line is an operating line. So it passes by this, and point O. So I'm gonna have a straight line that passes by O, the point on raffinate and point on extract. So this is gonna be a point on the raffinate layer. So I'm gonna take the equation from here and put it here. Again, we use the equations a lot, so you need to make sure that all the equations that you use are right equations and they represent the system well. So the other point on the line is gonna be the point O, which is this. And we can calculate the slope and the intercept now. I have everything, and I'm gonna do the same thing again. I have a point here, and I know the equation of the straight line now because I know 2 points, so I know the slope and the intercept, and I want to get the point of intersection on the extract layer. So to do this, I would take the extract layer equation and assume any value. I make like 5 or something. It looks like 5 here to me. It's gonna be something between these two, so it's gonna be around 5. And I'm gonna do one more goal seek. Just take this so I can tell easily that this is a goal seek cell. So it's gonna be this y that I'm getting from the extract equation minus the equation of the straight line, which is gonna be slope multiplied by x plus the intercept. And again, it's not right, so I'm gonna go goal seek, put this to 0 by changing this, and this is how it looks like now. So I'm gonna what I'm gonna do is I am going to shift this a little bit to the point or to the next row so that I can insert the new values here. So it's gonna be 19 and 5.77. You see, it's not a perfect straight line, so I can now oops. I think something is not right about this. Oops. Anyway, so I can add the trend line now, make it linear, and display the equation and display the r squared. So the equation is, as you see, is 0.5627 minus 4 point whatever. This is calculated from these 2 points. I want to extend it to this point here, which is the same number here, and I did the trend line just because I want to see how the r square will look like. So it looks like a very good straight line. It's exactly very good. I'm copying this and then paste as numbers. So I have the number of a slope and intercept, and then I'm gonna delete this. And when you delete this, it's the equation of a straight line. So the new values here that you see here and here are the values without the point in the middle and with the point in the middle. You'd see that the difference in the slope and the intercept is negligible. There is no difference. And I did this actually with 5 points. So I put here 1, 2, 3, 4, 5 and did the same thing. The equation was very close, 0.56605. It's 0.5627. It's in the third decimal place. Negative 4.74. It's negative 4.64. So it's exactly the same. So it's not or very close. I mean I'm doing this just to tell you that you can rely on the 2 points and use it as a straight line, and don't bother yourself by adding more points because it's not going to turn out to be a curve. I'm not sure if this is the case for all the systems or not, but at least for my system it was the case, so I don't need to worry about this anymore. So now you can go to the next step, which is calculating the number of stages, which is gonna be as simple as we did before for distillation. I'm gonna do a line from here to here, line from here to here, and again up and down till I reach this point. So this is what we'll see in the next video, inshallah. So I'll see you then. Goodbye.